Pick up a single uranium dioxide pellet and you'll notice it is about the size of a pencil eraser. It weighs almost nothing in your hand, yet that tiny ceramic cylinder holds the same amount of energy as a full ton of coal. Right now, millions of these pellets are sitting inside reactors all over the world, splitting atoms to keep the lights on in entire cities. Most people hear the phrase nuclear fuel rod and immediately picture a bomb. They imagine a pressurized stick of radioactive material that is one small mistake away from detonating. The real question we should ask is, why doesn't that actually happen? Why doesn't the rod melt, rupture, or run out of control? The answer has nothing to do with luck or oversight. It comes down to layers of physical engineering that are incredibly clever. And one of the primary safety systems isn't even mechanical. It's baked into the uranium atoms themselves. We'll get to that. But first, let's look at what's actually inside the rod. The process starts with uranium dioxide powder. Engineers compress it and fire it in a furnace at extreme heat, a process called sintering. It transforms loose powder into a hard, dense ceramic, like turning sand into solid stone. What comes out is small, dark, and incredibly stable. But here's a clever detail. The ends of each pellet are not flat. They're slightly dished, curving inward like the base of a soda bottle. That shape isn't cosmetic. When the pellet heats up, it expands. Those curved ends give it room to grow, preventing pressure buildup that could buckle the stack. It's the same principle as gaps in wooden flooring, design space for expansion. Now here's where it gets insane. A single reactor core can contain up to 18 million pellets. To match that energy with coal, you'd need a train stretching from New York to Los Angeles. So the real problem becomes, how do you stop that much energy from melting everything? The pellets are stacked inside a tube made of Zircaloy, thin as your finger, yet one of the most critical materials in engineering. Why? Because it's nearly invisible to neutrons. The particles that sustain the reaction pass through it like light through glass. But everything else, radiation, gases, byproducts, stays sealed inside. It's essentially a one-way barrier. Energy escapes, danger doesn't. There's also a tiny gap between the pellet and the tube wall, and that gap has to be perfect. Too small leads to expansion cracks the metal. Too large leads to heat gets trapped, causing meltdown from inside. Engineers had to calculate the exact balance that prevents both failure modes simultaneously. Inside that rod is a silent pressure cooker. Over 6 years, internal pressure can reach 2,000 pounds per square inch, greater than the bottom of the Mariana Trench. And the only thing holding it together is a weld thinner than a human hair. So how do we stop it from getting there? As the reactor runs, fission generates gases, xenon and krypton. These gases build pressure inside the rod. Without a release path, it would fail. So engineers added something simple, a spring. At the top of every rod is an empty space called the plenum. Gas escapes into this void. The spring keeps everything stable and compressed. No valves, no electronics, just a passive system absorbing pressure. That empty space is the difference between failure in hours and stability for years. But structural safety isn't enough. We still need to control the reaction itself. At the start of a fuel cycle, there's too much reactivity. So engineers add gadolinium, one of the most powerful neutron absorbers known. It acts like a counterweight, soaking up excess neutrons early on. Then, over time, it burns away, releasing control exactly when needed, like training wheels that fall off the moment balance is achieved. Here's the terrifying part. Across just a quarter inch, temperature drops by 1,400 degrees. In most materials, that would cause instant fracture. So what happens when everything pushes to the limit? This is where physics takes over. As uranium heats up, its atoms vibrate faster. That changes how they interact with neutrons. Their capture window widens, absorbing more neutrons without splitting, which means the reaction slows down. This is the Doppler effect in nuclear physics. Hotter core leads to weaker reaction. No sensors, no switches, no human intervention. The system self-regulates. In 1979, at 3 Mile Island, a cooling failure led to a partial meltdown. Operators misread instruments. Water drained away. It was one of the worst nuclear incidents in US history. But even then, Most fuel rods remained intact, gases stayed contained, and most importantly, the reaction had already begun slowing itself down before humans even realized the problem. 3 Mile Island wasn't just a failure, it was a stress test, and the engineering passed. Human systems broke, physical systems held. A nuclear fuel rod isn't a bomb, it's a system designed to become more stable as it gets hotter. That tiny ceramic pellet hasn't changed, but now you see what's inside it. A ton of coal's worth of energy, contained, controlled, and self-correcting. If you want to understand more hidden systems like this, hit subscribe. We break down one every week. And next, we look at what happens when even this isn't enough: the containment dome. Thanks for watching.